Let's talk about laminar or turbulent flow. So when we talk about laminar or turbulent flow, we need to go back to what Reynolds had done about it because it is the basic thing uh, how we can divide the turbulent flow and laminar flow. So it is the Reynolds dye experiments. It is a water flow inside a pipe, and then Reynolds used a dye which has a similar density with the fluid inside it, let's say water, and then because of the similar density, flow. Uh, the dye will flow with the water, and this dye will also show or the fluid field and phenomena like the water. So that's why we can use it to explain about the fluid phenomena inside the pipe. Okay, you can see here, if you talk about laminar here, you can see that the flow is uniform. There is no such as fluctuations. It is uniform and stable. And when we talk about transitional, at the beginning it is stable, but after some regions it will be fluctuated. And the last one, of course, it is turbulence. From the beginning, it is fluctuated and chaotic, and it is difficult to to predict the fluid flow phenomena inside of the pipe. And then Reynolds defines whether a fluid flow, laminar or turbulent flow based on what we call Reynolds number. So what is Reynolds numbers? It is actually the comparisons between viscosity force. Actually, it is here viscosity force, and here it is motion force, or sometimes or more common we call it as we call it as inertial forces. So it is inertial forces compared to uh, viscosity forces. That's what we call Reynolds number. And when we find the Reynolds number above or larger than 2100, sorry, when we find that the Reynolds number is smaller or similar with 2100, we call it as laminar. And if it is above 4000, we call it turbulent. And between these two numbers, we call it as a transitional. And the thing that you need to know, turbulent flow actually dominates in the most industrial applications. And it increases energy loss, but sometimes we need it because it also increases the mixing and heat transfer. So sometimes to we try to decrease the turbulent phenomena since it is about the energy losses, but also sometimes we use it for mixing and heat transfer. And then we talk about the other classifications of piping flow or pipe flow or internal flow. The first one, it is about developing and fully developed flow. So you can see here, a developing flow or entrance regions occur near the pipe entrance where the velocity profile is still changing. You can see here, actually, it is the entrance of the pipe, and then the fluid flow inside of the pipe, and this is what we call entrance regions flow, where the velocity profile is still changing. Look at this. Okay, this become from here it is uniform for example, and then because a little bit curved, and here it is fully curved. This is what we call velocity profile. So it is changing, and then fully developed flow regions, we can define it as a boundary layer have emerged. Velocity profile no longer changes with distance. You can see here the velocity profile is similar after uh, the flow after the fluid flow past the entrance regions. You can see here it's actually the profile is actually similar. Okay, and then what we need to understand at the fully developed flow, the pressure decrease linearly along the pipe. I think later I will show you about the pressure decreases linearly inside the fully developed flow. So how to calculate the entrance regions, because it's important for us to know where the entrance region flow. If the flow is laminar, so first we need to calculate the Reynolds number. And then if we find that the flow is laminar, we can use these equations. Okay, the length of entrance regions divided into the diameter of the pipe will be equal to 0.06 of the Reynolds numbers. But if we find that the flow is turbulent, we can use these equations. Okay, so it is actually different how we can how we can determine or calculate the entrance region flow. This is what I have talked about, the pressure distributions uh, at the entrance flow and fully developed flow. Sorry. So in here you can see at the entrance flow, this is pressure drop. It is not linear. It's not linear. You can see here, but at the fully developed flow, the pressure drop is linear. That's why we can define it as at the entrance regions, the pressure drop is not constant, but at the fully developed regions, the pressure drop is constant. A linear pressure drop in the fully developed regions is a clear indicator that the flow has stabilized. So after past the entrance flow, actually the flow has stabilized. You can see from this line. So what is pressure loss in pipe? Sometimes we can also use head loss. It's not just pressure loss, but also head loss. Okay. So what is this pressure head loss? As a fluid flows through a pipe, parts of its mechanical energy is lost due to first one, viscous frictions between the fluid and the pipe wall, disturbances caused by fittings, valves, bends, and other components, and this energy loss appears as a drop in pressure or head along the flow directions. We can see from the energy equations or Bernoulli equations between two positions along the pipe. For example, pressure at the first position and pressure at the second positions. Okay, we can see from these equations that at this, along the pipe we will get head losses. This is how we put the head losses into the Bernoulli equations. And the thing that you need to know actually, if you talk about head losses, we have two different losses. The first one, we have major losses. The symbol is HF or HL major, and we calculate major losses based on these equations, which is it is the friction factor, it is the length of the pipe, it's that the diameter of the pipe, and the velocity and uh, gravitational accelerations. And with minor losses, we don't need to calculate the frictions because normally we get the minor losses from fittings, valves, or bands, or I think what we need in this equation is just the coefficients of the minor losses. So we can also use that the coefficients of major losses is actually F, L, and D. But in minor losses it is only K. Okay. So this is the two different losses inside of the pipe. So when we talk about total head losses, we need to calculate both major losses and minor losses.